Hello, everyone. Today is a special lecture in which I hope to present my research together with my postdoc Changhu Wang, who is here today for about something related to our lecture. So in the lecture, we talk about linear model, and we talk about that we can test whether each coefficient is zero or not using the t-test, right? And we can calculate p-value for the t-statistic for each predictor. And then we can talk about how to decide which predictors have non-zero coefficients. So I briefly mentioned about this multiple testing problem in my lecture. And today, the research talk I hope to share with you and also welcome your feedback is we propose an alternative approach to generalize this problem, especially in the scenario where p-value calculation is not easy. So this work, we title it as SyNPar, standing for synthetic null parallelism. So I'll explain the term later, but our hope is to achieve high power and fast control of false discovery for selecting important features or predictors. So the setting here is that we will have a prediction model with P features. So I'll just use the term features throughout my talk today. And end observations. So this Y is our response. This is the setup we are familiar with. And so here, the problem we want to discuss is how do we know which of the P features have non-zero effects on the response? And to answer this question, because we may make some mistakes in our identification of the features, we hope to balance two quantities or two error rates. False positive rate, which is how many features are found as false positives. And for this one, the rate is commonly used as false discovery rate, which I will define in a later slide. We also briefly mentioned that in our discussion of multiple testing. The other is the number of negatives. That is, we hope to have this number also small so we can achieve high power. Specifically, under a linear model, we can write in this way, and this is the form we have used, the matrix form we have used in our class. So here we denote the true coefficients as beta star, and among the P features, there is a set we call signal features that have non-zero coefficients. And there's another set we call null features, which have zero coefficients. Typically, the signal feature set is small when the size is much smaller than P, and the null feature set is bigger. And we also need to assume the error term follows some distribution. In our class, we also use this distribution, the simplest one. That is, the error terms are independent and have the same variance sigma squared. If we want to be more general than this linear model, we can use this general writing to say there's a model for generating y conditional on x, which is the fixed design scenario we talk about in our class, given the true coefficients beta star and some nuisance parameters. So in the linear model, the nuisance parameter is just sigma squared. It is not our parameter of interest, but it is something we must account for. So the linear model is an example of a parametric model. So we can later in our class, we'll talk about generalized linear model as the GLM, or GGM stands for Gaussian graphical model, is not part of our class. And we can also have the nuisance parameter to have infinite dimensions, like in semi-parametric models. So beta stands for the parametric part, while this infinite nuisance parameters stand for the non-parametric part. Like Cox regression, if you have heard about it in survival analysis, is an example of semi-parametric model. So our discoveries will be denoted as a set S star, which is a subset of the P features. So false discovery rate, as we briefly mentioned before, is a quantity or criterion for multiple testing problems. So it is a quantity that aggregates the results from all tests. It is the expectation of this ratio. And in this ratio, people call it false discovery proportion. So rate becomes proportion inside expectation. The numerator as the number of false discoveries, which is the intersection of our discovery set and our null set. So these are false. And the number of discoveries. So we take at least one in the denominator to make sure that we don't have a dividing zero issue. So for p-value based FDR control, this is the procedure Benjamin Hochberg used in the original paper that introduced FDR. So you need to have a valid p-value for each test, and then the BH procedure will give you a threshold on the p-values. However, the BH procedure assumes that the p-values are independent, which may not be the case because your different features may have some dependence. So then to account for the positive dependence scenario of features, there is a BHQ procedure or BY procedure. This is more conservative in terms of FDR control. So if you have features independent, you can still apply the BHQ procedure, but you will get a smaller FDR than what BH gives you. But if we have a high dimensional setting, which is something we haven't covered in our class yet, and this is about when P is larger than N. So in the class, all the settings have N larger than P. So it's a large sample size setting. We have a fixed number of predictors or features, and our sample size can go large. But in the high dimensional setting, that is, we have more features than our sample size. Then what do we do? So some people, you might have heard of the lasso method for selecting a small number of features from the P features, but you don't do test with lasso. Basically, lasso just give you non-zero coefficient estimates and you find those features. But whether those coefficients you find with non-zero coefficient estimates are truly non-zero or not, that remains a question. So you could use lasso to select features. So now the feature number is less than n. And then you do testing using our regular procedure like the t-test we introduced for ordinary least squares. But then there is a double dipping bias, which is something we should be aware of because we're using the same data for twice, first for selecting the features and then testing. So then the test is not as a regular case. So to avoid this problem, there is a method called d-bias lasso, which will give a different parameter estimate from lasso. So different from lasso, it will give you a different beta hat as estimate, and their beta hat J will have some asymptotic distribution you can use. But first of all, d-bias lasso takes a long time to run, and second, the null distribution is asymptotic. So if your sample size is very small, it may not hold very well. So to address these challenges with p-value calculation, there is a line of literature in recent years called the knockoff filter. So the idea is very interesting. So basically, we want to construct knockoff features. So we call that X tilde. It is the same dimension as our design matrix n by p. So the goal is to have the knockoff features in this X tilde, the p knockoff features that have no effect on our y. But these features have the same correlation structure as the original features in X, and also you can swap original features and the knockoff features between the two matrices without changing the property of fitting a joint model. So you can fit the original feature matrix and this knockoff matrix by this concatenation. You concatenate them by column, so you get an n by 2p matrix, and then you fit a linear model. So then you can use the coefficient estimates of the original features and compare with them with the knockoff features to decide whether the original features really have non-zero coefficients. Because you know the true coefficient for x tilde should be zero, even though your estimate is not zero, but that is due to the estimation inaccuracy or the randomness in your data. But you know that the truth should be zero. So that's why this x tilde feature, knockoff features, coefficient estimates will provide a negative control to the original features coefficient estimates. So how to generate a knockoff? The original one is under the fixed design scenario we cover in the class, but it's only for the low dimensional setting. You must have n at least twice as large as p. So it's not a high dimensional setting. For the high dimensional setting, model X knockoff is used, but its generation is quite complicated. So basically, this knockoff idea is to work with concatenated data, not the original data. And in parallel to knockoff, there's a line of literature called Gaussian mirror. It started with Gaussian mirror. So the idea is also very interesting. Instead of generating knockoff features, it tried to convert each original feature into a pair of mirror features by some perturbation. That is, we add a small Gaussian noise to each feature and we subtract the same amount of Gaussian noise from each feature. So these pair of mirror features will both be, how to say, they should be similar to each other. And then we can use them to see, oh, if a feature is not, how to say, significant, then their mirror features coefficient estimates may be one positive, one negative. We can see that they are surrounding zero. But if a feature is significant, it has a strong non-zero coefficient, then its mirror features should have coefficient estimates with the same sign, even though they differ a little bit by magnitude. So that's the intuition behind it. But to do this Gaussian mirror, we need to generate one mirror feature pair per original feature, and we keep the other features unchanged. Then we fit two linear models to the two data sets, one with one mirror feature. So basically, we create a pair of data sets by perturbing one feature. But then you can see that you need to do this for each feature. So for each feature, you need to perform two model fittings. And then in total, you will perform 2 times P model fittings. And that's computationally intensive. So later, the same authors proposed to perform data splitting. So that is, instead of generating mirrors, I just randomly split original data into 2 halves by sample size. So n/2 sample size in each half. Then we apply the same parameter estimation procedure to the 2 halves in parallel and compare the coefficient estimates in the 2 halves. And then using that, we compare the coefficient estimates to find the features with FDR control. But since splitting data once may not be stable, that will give us randomness. Then they propose multiple data splitting. So we can do the splitting for maybe 50 times or 100 times. So our motivation for this line for our research is starting from this real data analysis. So this is a data set where we have N as 150 samples, P with more than 6,000 omics features. So this is a high-dimensional data set, and the goal is to predict the time to labor on set. And the features are from proteomics data, metabolomics data, and mass cytometry data. So the goal is to identify important biomarkers associated with time to labor onset. So if we run MDS or Model X knockoff on this dataset with 70 replicates, since both procedures involve randomness, right? Random splitting or random knockoff generation. We want to check their stability and in each run, how many features are identified. But surprisingly, MDS consistently identifies 0 features, no signals found. Model X sometimes found 10 or 15 features, but for the majority of times, 0 features. So this will give us some intuition or guess that there might be a low power issue because they don't find many discoveries. And our intuition is that the low power was due to the alteration to the original data because they're not fitting a model on the original data. Instead, knockoff fits a model on the concatenated data, where the P original features are concatenated with the P knockoff features. And we know the P knockoff features have no signals. So you're adding noise to data. While the DS only fits the model on 1/2 of the sample size. So you also lose the quality sample size. So both alterations decrease the quality of the original data. So therefore, with the poorer model fitted on poorer data, we think there will be a reduced ability to discover true effects. And then we have low power. So this issue has also been mentioned in this JASA paper, in this data splitting paper. So the question we have is, can we develop a method that uses a model trained on the original data without such deterioration? So our motivation came from two reasons or two motivations. One is our research in the single cell field. So this is a work we developed called cluster DE. in which we try to address the double dipping problems where the data are first clustered into two groups. We call them two cell types, and then we try to perform the two sample comparison, like two sample t-tests between the two groups. But as the two groups are from clustering instead of from original definition or predefined groups, there would be some inflation false discovery. So our approach is to generate a synthetic null data set with just one cluster and perform clustering and the two sample tests on this data set in parallel to the original data set, and then we do comparison of the result. So this is a parallel approach. We generate data under our null hypothesis that there's only one cluster. But in addition to our work, there's another work trying to address the same problem, but it uses the knockoff approach. In other words, it will create a concatenated matrix n by 2p instead of two parallel matrices. And then on this large concatenated matrix, it will perform clustering and differential expression or two sample test. So this made us wonder which approach might be more reasonable, parallel, or concatenated. Since we question the deterioration of data quality by concatenation, then we doubt maybe parallel approach is more reasonable as the original data is preserved. The second motivation is the likelihood ratio test we have covered in our class. So we said that we can do the likelihood under the null hypothesis, under the alternative, and we maximize the likelihood by maximizing the parameters values right under each null hypothesis or alternative hypothesis. Then we compare the two ratios. So you see, this is like a parallel approach. We have the data there, but we compare two models. So each model, we give it a likelihood and we compare the two likelihoods. So here our question is, can we generalize the idea by not saying, oh, we just compare the likelihoods, but can we turn the likelihood into a data set? So the alternative hypothesis without constraint, we can just use our original data. That's the no constraint case. But for the null model with constraint, can we provide the data that looks like the original data, but it's under the null hypothesis? So that's our motivation for this synthetic null data parallelism. So first of all, I want to define what do we mean by synthetic null data. So in the model, the general form of the model, the design matrix is fixed, but we hope to generate the response under the null coefficient, right? The beta, we call it beta 0 to mean that it reflects the null hypothesis. But how about the nuisance parameter? We don't observe that. So we will still want to estimate the nuisance parameter from our original data and together with the coefficient estimate from the original data. But we want to modify this coefficient to reflect our null hypothesis. Okay, so that's the general idea. But we will be more specific about what the null hypothesis is later. So how do we perform the estimation on both data set with the original data, which is y and x, or the synthetic null data, which is y tilde x? We need an estimation procedure. So our idea is to use whatever procedure of choice, use it in the same way on two data sets in parallel. And we call the original parameter estimate as beta hat and the synthetic null parameter estimate as beta tilde. So in other words, we hope that beta tilde can serve as a negative control for us to identify what are the coefficients, what are zeros, and what are non-zeros in the original data, true parameter. But we have to see that as if the beta star, the true parameter is have zero components, the beta hat components corresponding to them will not be exactly zero because of the estimation error. Similarly, if we know beta 0, the true null parameter have zeros, then beta tilde will not be exactly zero because of estimation error. But we want this beta tilde to be a little more conservative or to be more to have larger absolute values than their counterparts in this beta hat. So we can have an overestimate for false discoveries if we want to threshold beta hat for discoveries. So in other words, the discoveries will be made on beta hat J by absolute value. We want to have a threshold so that the J components with absolute values greater or equal than T will be the discoveries. But we don't know this, right? So how can we control this quantity? And if there are false discoveries. So we want to say that for any null features and for the magnitude of their beta hat J greater or equal than T, that means they're false discoveries. We hope that they occur less frequently than in the negative control case. So in other words, we hope to have more expected number of false discoveries on the negative control than on the original data. So therefore, this negative control offers an overestimate for the number of false discoveries in the original data. So that is the problem. That is the goal. So in other words, given the same threshold, we hope the negative control to have heavier tails than the original estimates on the null features. So we consider two types of null hypothesis: the global null, in which we set all features to have zero effects. And this is simple because we just need to have one model and generate the synthetic null data from this one model. So in other words, we just need one model fitting to get a nuisance parameter from estimate from the original data and then generation. But this may not be what we want, right? Because like in our class, we may be more interested in individual null hypothesis. In other words, we just set one component to zero, but keep the other components unconstrained. So in this case, we can also implement it as by setting the jth component of beta 0, the null parameter to 0, and estimate the other components from the original data. So if we do that, then given this individual null, we will generate one response in that case, and then we apply our estimation procedure to the synthetic null data just for feature J to get the beta tilde J. And we have to do that by going around all P features. So P fitting, P model generation, for synthetic null generation, P parameter estimation. And this will be computationally intensive, as is for the Gaussian mirror case. But we use it as the baseline for comparison. So our hope is that the global null may be something useful so we can have an efficient procedure. And let's see whether we can do it. So first, we implement a simulation under this not so high dimensional setting. So we have n as 300, p 200, and we also generate a design matrix by allowing features to have some correlations. So ignoring the technicality here, basically we have one parameter row to control the adjacent columns in X correlation. And we set the first 30 features to have non-zero coefficients as 0.3 with random positive or negative signs, while the remaining coefficients are set to 0. So we first compare our global null approach to individual null approach, but just on here because I will specify what we did for global null later in detail. So for global null, we need to do some modification, which will be specified later. But with that approach, we can see that global null is actually not necessarily bad, worse than individual null. So even though if the global null and individual null, they both control the FTR under the target 0.1. But in terms of power, when features are more uncorrelated, individual null has some higher power advantage, but when features are more correlated, the global null actually has an advantage. This also makes sense if you think about the feature correlation. If they're more and more correlated, then individual null hypothesis will become more like global null hypothesis. That is, if one feature has zero coefficient, then other features also tend to have zero coefficients. So then the global null just captured them all. But you can see that when the individual null has power advantage, their difference is something very small. But if the global node has advantage, there's actually a bigger power advantage. So based on this simulation and also the computational efficiency of the global node, we will focus on global node for the rest of my talk. So as I said, for global node, there's a key thing we need to clarify or we need to make the procedure work. That is, we need to add a correction factor to enlarge the absolute values of our negative control coefficients so that we can make it a conservative estimate to allow for estimation error. So as we said, in beta star, there are certain coefficients that are zero. In beta zero, for global null, all coefficients are zero. But for those zero coefficients, beta hat and beta tilde are not necessarily zeros due to the estimation error, right? So how can we make sure that beta tilde absolute values can upper bound beta hat absolute values? So our approach is to consider the infinity norm of both differences. It's because the infinity norm captures the largest absolute value difference between the estimate and the true parameter. All right, so we can say that the first assumption we need for our procedure to work is that there exists a high probability upper bound on the estimation error. So to do that, we need to assume that the nuisance parameter estimate lies within a compact set. So there's no boundary case for special consideration and asymptotically. And second, we need to ensure that there exists such a gamma NP that provides a high probability upper bound on the infinity norm. So with such factor exists, and suppose we can find it, then this factor can be used to inflate our negative control absolute value so that we can satisfy this quantity, that is this numerator of our FDP estimate, false discovery proportion estimate. So we're using the number of negative control coefficient absolute values after inflation, after correction, larger or equal than the threshold as an overestimate of what are the false positives of using eta j hat greater than t for making discoveries. So we believe that among these discoveries, the number of false discoveries is controlled by the numerator and the expectation. Okay, so using this FTP hat, we search for the data-driven threshold T. That is, we want to go with the minimum T so that we can have the FTP hat under Q. Then Q is the target FDR, say 5%. So essentially, setting the T to be the minimum that satisfies this threshold, we can maximize our number of discoveries. And then our number of discoveries are based on comparing our original data coefficient estimates absolute values to this threshold. So you see this side involves only our original data. Only the threshold involves the synthetic null data. There is an alternative approach for doing the thresholding. Instead of directly thresholding the original coefficient estimates parameter estimates absolute value, we could take the difference between beta j hat absolute value and beta tilde prime j, the inflated negative control absolute value. So this difference and thresholding it has been widely used in like knockoff procedure. It's the standard way to do that. But the reason we only consider this as alternative is because here the WJ involves the random error in the synthetic null data, randomness, while here the beta J has no random error. So therefore, here when we use the threshold determined data-driven way, same idea, and compare WJ to the threshold, we see both sides of the inequality involve randomness. So we have the procedure for doing the FDR control, but how can we know whether the FDR is controlled? So to do that, here we don't need to assume that features are independent, but still the features cannot be so strongly dependent. So this is a technical condition just to ensure that yes, feature weak dependence is okay, but it cannot be too strong. So like the variance of the sum of this indicator function of feature j. So we sum over indicators, sum over feature j. This sum cannot be in the order of p squared. Because if the features are totally identical or completely independent, the variance of a sum will be the order of p squared. That's something we cannot tolerate. But we need a sum variance of the sum of indicator to increase slower than p squared. And for both the original estimates and the synthetic null part, negative control part. So this is a technical condition. So with that, we can have the theoretical result to have asymptotic FDR control. That is, we know that using our procedure and satisfying the two assumptions, one about the existence of the correction factor, one about weak dependence. Given the way we define the threshold and we select features, as our sample size and feature number both go to infinity, then we can now have the FDR less or equal than Q plus a shrinking constant. So this constant goes down to 0, small o1, as n and p goes to infinity. So this can ensure that asymptotically FDR is controlled. And furthermore, if we have the minimum signal strength high enough, that is 3 times the correction factor, then we can even have asymptotically perfect power. So as sample size go to infinity, we can actually have the power approaching 1. So that's the theoretical result to show that it is something with guarantee. But conceptually, if I want to compare our approach SyNPar with existing approaches, we can summarize the approach for generating contrast with the original data. So we do data synthesis like knockoff, we generate data, while Gaussian mirror perturbs the original data, and data splitting splits the original data. And given that we have the contrast data generated or obtained, how do we do the comparison? So SyNPar, Gaussian mirror, data splitting all do the parallel comparison, while knockoff does concatenated data. So later, I will use linear model as a concrete example to show more results. So for linear model, how do we generate the synthetic null data? So one approach is that we just try to estimate sigma hat from the original data, and then we just randomly generate the errors from this fitted error distribution. This is our Nielsen's parameter. And for the global null, we just set beta 0 to 0. So therefore, y tilde is just our generated errors. So this is our synthetic null data. And if we use lasso as the estimation procedure on both data sets, original data, synthetic null data, with this lasso tuning parameter for sparsity, regularization chosen by cross-validation on the original data, and we use the same lambda n on the synthetic null data. And so for lasso, there is theory to guarantee that the high probability upper bound on infinity norm exists, and it's in the order of this root log p over n. And this is a standard result in high-dimensional statistics. And lambda n is in the cross-validation. It's also on the same scale, on the scale of log p over n, root log p over n. And there's a constant there. So in our numerical results, we set this constant to 0 times 2, 0.2 times sigma hat based on our empirical evidence. But I will say that how to choose this correction factor is the most crucial thing for our procedure. So we considered a lot of settings under simulation setting 2 by considering the feature correlation parameter and the signal amplitude of non-zero coefficients in beta star and the target FDR level and the feature number. So we consider all these things. And we have a default setting. So by changing one parameter at a time, we set the other parameters at these values, and we set the first 30 elements to be non-zero. All right, so first of all, we have to say that SyNPar runs much faster than existing knockoff approaches. Model X knockoff, fixed X knockoff, if it satisfies a low dimensional setting, data splitting, multiple data splitting. Only data splitting is fast, but multiple data splitting is more stable. So the following are a series of simulation results. So first, as we change the autocorrelation coefficient, we can see that almost all the methods, and here we also consider p-value based methods using BH or BHQ procedures. So almost all the methods have reasonable FDR control. But if we look at power, our approach, the two, so basic SyNPar and SyNPar diff have high power, especially SyNPar has even higher power than SyNPar diff. So the default is to use SyNPar. And also we can see that the power gain in here is that our SyNPar has FDR slightly increases, but still under the target, and this can make the power higher. While if you compare that to knockoff, you can see that knockoff have FDR higher when there's little correlation, but it has low FDR when there's a lot of correlation, and their power also goes down. So, and the second thing is regarding the signal strength, signal amplitude. So with the methods all controlling FDR, we can see that our SyNPar, especially SyNPar default version, has the highest power compared to Model X, Fixed X knockoff, data splitting, and BH. And finally, we change the target FDR to check whether the FDR are consistently controlled, yes, and also we compare the powers. SyNPar still has the power advantage. And finally, number of features. So we see that the power advantage of SyNPar still holds, and also the control of FDR. Especially, we see that the SyNPar has less sporadic changes as P number changes compared to Model X knockoff in terms of FDR and power. Finally, we look at the AUPR, area under precision recall curve. So this shows the overall accuracy by balancing FDR and power, and also across different thresholds, and not at one FDR threshold. And we can see our AUPR is also better, which confirms the better discovery power. Another aspect we consider is the stability of the result. That is, all the procedures, SyNPar, Model X, DS, and MDS, has randomness in their procedures. Then we can run them for many times. We do 100 times and compare the intersection size of their selected features versus the union of the selected features. And surprisingly, you can see that SyNPar has a much higher advantage over other methods. Model X has 0 Jacker index because sometimes it will return 0 features, while SyNPar has very high consistency because SyNPar is only changing the threshold tau q, while the beta hat j from the original data's coefficient estimates stay the same. Okay, and we also check what if we change our synthetic null data generation procedure. And here we generated from a more heavy tail Laplace distribution to be more conservative. And then you can see that in this case, we can still control the FDR and maintaining quite good power using this more conservative approach for error distribution generation. And finally, we consider other estimation procedures besides lasso, including SCAD, elastic net, ridge, and we of course need to choose the appropriate correction factor. And because we haven't done it in a data-driven way yet, so here we just try to set the factor in an empirical way. And we say that we can consistently control the FDR and having very good power, especially lasso consistently have very good power. So that's why our default estimation procedure is lasso. Finally, our simulation setting will involve the real data we first introduced. The real data has a small sample size, large P number. So what we did is that we just tried to use lasso to obtain the coefficient estimate, using that as the true coefficient. And we also set the coefficients below a signal threshold to 0. So we have many zeros and small number of 30 non-zero coefficients. And the error variance is estimated from real data. So then we use the error variance and the beta, we set it this way to generate Y from a linear model. And the design matrix is from the real data. So On this data, we use the same correction factor we said before. And you can see that comparing SyNPar Model X to MDS, one notable difference is SyNPar has much shorter running time and also much higher power and AUPR than the other two procedures. Especially the power advantage is very obvious. So on this data, real data, we can see even bigger difference than previous simulation settings. And in terms of the real data, when we apply to the data, we can see that SyNPar consistently have feature discoveries, while Model X have many cases no discovery, MDS consistently no discovery. And we can also see that if we use the selected features to run the prediction model and to calculate adjusted R-square regarding prediction accuracy, then SyNPar is also the highest, the feature selected. So to conclude, we propose a method called SyNPar to preserve the original data and to address the feature selection problem by generating synthetic null data. So the major advantage is for its high power and computational efficiency. And it has the key components, including the ability to generate synthetic null data. It should be three key components: an estimation procedure for estimate beta, and finally, for the parallel contrast. The data generation procedure is very related to parametric bootstrap because we need to fit a parametric model and then generate data from there. But unlike parametric bootstrap, we set our parameter of interest to the null case. That is different from the bootstrap. You don't change the parameter to the null case. For the parameter estimation, we allow flexible procedures. For the parallel contrast, this parallel idea is similar to likelihood ratio test because we're doing the same, using the same data, but we fit two models. And for I think this is a more general cost simulation-based inference framework. So that can allow us to leverage synthetic data instead of working with likelihoods for parameter inference. And finally, I want to say that for future direction, we hope to extend it to more models and algorithms. I just talked about linear model in this talk, but we already have results for a few more models. And second, we hope to develop data-driven methods for choosing the correction factor in practice. And there will be also emergent theoretical questions to be analyzed under this framework. And regarding the application to the field I work extensively, bioinformatics, I want to say that many algorithms are black boxes, and we hope the synthetic data can make analysis more rigorous by controlling the FDR and evaluating the stability of discoveries. So finally, I want to thank my postdoc Changhu Wang for leading the efforts of this idea and for all the results, and also the master student Ziheng Zhang, who is a biostat master student who has been helping with the simulation numerical experiment. And thank you very much. So I think Changhu will be here to stay around and hopefully to answer your questions. And then I'll see you next week. Thank you.